Thank you for joining us virtually for Science Odyssey 2021 from the UBCO Okanagan campus. I'm Professor Jen. Joining me today is Maxine and Eli. We are the iSTAND team, and this is, with great reflexes comes great responsibility. Maxine, Eli, what are you guys doing?
My doctor's testing my reflexes tomorrow, so Eli's helping me practice.
Seriously? That's not reflexes, guys, that's reaction time.
Wait, so what's the difference then?
Well, we can answer that question with science. More specifically, neuroscience.
What is neuroscience?
Neuroscience is the study of the nervous system, and the nervous system is composed of the brain, the spinal cord, which is housed in the bones in the back of your body, and all of the nerves in your body, some of them shown here, coming out of the spinal cord. The nervous system's really important because it controls what we do, how we move, how we think, and even in how we interpret what we see.
The cells in the nervous system are called neurons. Neurons are string-like cells, and some can be really, really long, even as long as your entire leg. These cells communicate with one another by sending chemical messages across the gaps in between neurons. When you have a bunch of neurons connected together like this, they form complex networks called neuronal networks. These networks are what help us think, feel, see, and move.
Reflexes and reactions are part of neuroscience. It's something we get to study. Reflexes are circuits, and they happen really, really fast. Reaction times are also fast, but they're a little bit slower than a reflex.
What do you mean by circuits?
That's a great question. So a circuit is a system that allows things to interact together. Let's look at an example. So a knee-jerk reflex. In neuroscience, we might call this a tendon tap or a monosynaptic reflex. That's a pretty big word. But what happens, you might have seen this at the doctor's office, where they tap the tendon just underneath your knee. And when they tap that tendon, the muscle stretches. You can't even see the muscle on the front of your thigh stretch. But that muscle, when it stretches, sends a signal to your spinal cord. That's called the sensory neuron. And in the spinal cord, it doesn't touch, but it communicates with another nerve that's close by. That's the motor nerve. That motor nerve then sends a signal back down to the muscle that was stretched and says, shorten. I'm not supposed to be stretched. That is why when a doctor or even someone in a lab taps your tendon, why your leg kicks out and then comes back in, because the muscle stretches and involuntarily it's contracted or shortened.
How is that different than reactions?
The main difference between a reflex and a reaction is that a reaction involves a little bit of thinking. Reflexes don't involve any thinking at all. So with a reaction, there has to be a planned outcome. In a reflex, the outcome isn't planned.
Why are reflexes faster than reactions?
Since reflexes involve simple circuits, sometimes just two neurons connecting with one another, they can be very, very fast. Reactions involve all these other parts of our brain talking to one another and sending signals back and forth, so that takes a little bit more time for the response to occur. So in a reaction, all the different parts of the brain are talking to one another and they're trying to decide which response they need to generate. It's all of these extra steps that cause a reaction to be a lot slower than a reflex. It's important to remember though that even though we say reaction times are slower than reflexes, reaction times are still really, really fast, usually less than a second. So what we have here is a little experiment that's going to show you the difference between reflexes and reaction time. On my leg I have these stickers which are attached to wires. They go to this little device right here that's plugged into my computer, which you can see on the screen behind me. So what's happening with this little setup is that every time I kick this leg out, you see a big burst of spikes show up on the green tracing behind me. Whenever I kick this leg out, you see a big burst of red spikes behind me. So what Maxine is going to do is Maxine is going to use what's called a patellar tendon hammer. And she is going to tap my tendon, which is this little part of my body right here, very fast. When she does that, that's going to engage what's called the stretch reflex. So a stretch reflex happens when the muscle is stretched very fast, and that's what's happening with the hammer. So the hammer is tapping the tendon, and it's going to stretch the muscle very fast. When that reflex is engaged, the signal goes from some stretch receptors in my muscle up to my spinal cord, which then sends a signal down to my muscle to contract. So now what we're going to do is we're going to do the exact same experiment, except there's going to be the reflex happening on this side of my body, and then I'm going to react to the tap by kicking this leg out on the other side of my body. So what you should see on the screen is muscle activity from my right leg and muscle activity from my left leg, and we're going to see which one's faster or which one happens sooner. So we've paused the recording on the screen behind me. If you look at the bottom green tracing, you'll see some big spikes occurring. And then shortly after the big spike happens in the green tracing, you see a burst of activity in the red tracing. Remember, the green tracing is my reflex, so it's happening very fast. The red tracing is lagging behind the green tracing, so it's taking a little bit longer because the reaction that my leg is giving is actually coming from my brain rather than my spinal cord.
Can we make our reactions as fast as our reflexes?
Our reactions and our reflexes differ in speed because our reflexes occur automatically and our reactions need a little bit more thinking. For our reflexes, we don't really need our brain to be involved. It's a little bit like pressing dominoes that are all in a line. Once you hit the first one, they all just go. Whereas with your brain, you kind of need to decide, well, what is it that I'm reacting to? And what should I be doing to this? And how do I go about doing that? So those all slow down the speed that your brain can react to. With practice, we can make our reactions faster. When we first learn a skill, our movements aren't very accurate, and we have to keep looking at what we're doing so that we can make the right movements. To make our movements smoother and more accurate and more efficient, so we don't need to keep looking at what we're doing, our brain sends really clear instructions to our muscles, and as we practice, those instructions get clearer. So the more we do something, like practicing, the more opportunities the brain has to kind of refine all of these instructions. Did you know that it could take up to 10,000 hours of practice though for you to be an expert at something? Think of all the times your brain has had to change those instructions to be just perfect.
Here's an activity you can try at home or in the classroom.
So now that you know what reactions and reflexes are, you're going to make your own reaction timer to see how fast your reactions are. So first, make sure you have a partner and grab a ruler. Then I'll get Eli to help me demonstrate. So one person will hold the ruler at the top, make sure that there's 0 at the bottom, and then you're going to drop it, your partner is going to catch it, and you're going to measure the distance that the ruler fell. So the distance that it fell corresponds to how fast your reaction was. So if the ruler fell all the way down, your reaction time is pretty slow. If you caught it right at the top, great job. So have fun.
Thank you for joining the iSTAND team from UBCO Okanagan for Science Odyssey 2021.